We're going to be dealing a lot with vectors in the rest of this course, so I want to make sure I give you guys a clear sense of what a vector is. And I'm taking the definition from this book, A Vector Space Approach to Geometry by Melvin Hausner, which I really like. So he starts off by saying a directed or oriented line segment is a line segment with endpoints in a definite order. So if you look at this segment here, there's a line from P to Q, and there's an arrow here. If you've taken geometry classes, you might be familiar with the concept of rays, but this is not meant to be anything like a ray. A ray starts at a point, and the arrow indicates that it goes on forever and ever. This is a segment. It starts at P and it ends at Q. The arrow indicates the direction of the segment, that it goes from P to Q. So let's see. So here we have, So here in this diagram is showing the directedness. A vector is, so if we had it, we could also imagine a vector going from Q to P, right? That would not be the same vector because it's in an opposite direction, or would not be the same directed line segment because it's going in a different direction. It's not directed the same way, right? So a vector is kind of like a line segment, but when we talk about vectors, we say that two directed line segments, basically two directed line segments that have the same length and direction, are considered to be the absolutely same vector. So the way to think about this, the way he explains this is you could think of P and Q as two components of a sum, right? So you can have a sum P plus Q that adds up to a particular number, but your P and Q could be very different. So you could have 3 and 7 determine the number 10, but so does minus 1 and 11, right? So these two different components, even though they're different, 3, 7 is not the same as minus 1, 11. These different components can determine the same thing. It's the same idea that you could have two directed line segments that have the same length and the same direction, even though they start in different and end in different points in space. They're considered the same vector. Okay. So the idea is, if you could just slide P and put it right on top of Q without rotating it or anything, then and they perfectly aligned, then they're the same vector. And making it a little more formal, you could say if PQ is parallel to P prime Q prime, and the length of PQ is the same as the length of P prime Q prime, so these are parallel, they have the same length, and their orientation is the same. They both start at P and end at Q, then they're equivalent. And they're the same vector, basically. There's a little bit more to it that he wants to be clear about. So one thing was with this idea of parallel. So typically, when we're talking about parallel, we usually mean, a distinction is made between parallel, coincident, and intersecting lines. And when you get into 3 dimensions, you can also have skew lines that don't have the same direction, but they also never touch. In terms of vectors, what the author's talking about when he says parallel, he's using parallel and coincident, parallel to include the case of coincident. So you can have, a vector that, is basically we would consider this directed line segment PQ to be parallel to itself, basically, is the idea. So as long as the direction is the same and the length is the same, we're good, right? Also it's possible we want to include the case of a zero length vector. Okay, so in other words, it starts at P and ends at P. And so in that case, we really can't use A and C here. We can't use parallel or orientation. But if they both have the length 0, we consider them to be the same vector, and that's called the zero vector. Okay, so that's a special degenerate case. So after that discussion, let's see, is there anything else? So, any 2 points, P and Q, can determine a vector from P to Q. Okay, basically. So that makes sense, right? So any place, so if you could imagine a Cartesian coordinate system in here, from any one point on another point in that coordinate system, you're defining a vector. And you could define the same vector, again, you could define the same vector, and starting at infinite many points, as long as you're going for the same distance in the same direction. Those would all be the same vector. We said, so if we start at P and end at P, that's equivalent to starting at Q and ending at Q. So that was our case where we have a zero vector. And this is a good point too. If we have a vector that starts at point P and ends at point Q, and then we pick another point in space, P prime, there's exactly one point, Q prime, that will make this vector parallel, that will make the directed line segment P prime Q prime parallel to the directed line segment PQ. So there's only one way to make an equivalent vector. And then he talks a little bit about the notation. So you'll see notation in the textbook is they'll bold, use bold print for vectors. When it's written out, and you'll see this in videos where the professor's writing up on the blackboard, we would write a vector like this with this little arrow up on top of it to indicate it's a vector. The zero vector would be written like this. And there's also this thing called a unit vector, which just means a vector that has length 1. And that's usually written with a little caret on top of it. So that is your intro to vectors.